All right, let's see if it holds on. As I was saying, we have a line. Every point can be looked at as a vector, all right? And the more points we have, right, we can represent them. We have basically an infinite number of vectors, right? Now, each of those vectors, I mean, this can't just be an arbitrary vector. The vector has to go to a point on the line. So there has to be some way of generating those vectors, right? I mean, some way that we can produce all those vectors. Just like for the equation of a line, y equals mx plus b, there is a way of producing all of the ordered pairs. Yeah? Okay, so here's how we're going to do it. All right, it's going to be a buildup. What we're going to do is we're going to create what's called a vector equation of a line. It's different than a normal equation. Normal equation of a line, y equals mx plus b. Y equals mx plus b does not have a vector in it, right? Y is the variable y, m is a slope, it's a number, right? X is a variable, and then plus b, b is a number. So there's no vectors involved there. What we want is this new thing called a vector equation. So there should be vectors in it. The vector equation of a line is an equation which generates all the vectors from the origin to every point on the line. So what we just saw in that picture. So let me focus by first just trying to generate one vector, all right? One vector. So the origin is the point 0, 0, right? And let's just say that this point up here is the point x naught, y naught. X naught, y naught. So let's say I know one point on the line, right? Then the vector x naught, y naught is the vector going from the origin to that point, correct? Okay, so we start with that. We will call that r naught. That's our first vector. Now, let's say that we had another point on the line. So we had 2 points on the line, which is what we needed in college algebra to define a line, right? 2 points. So it's not crazy to think that we might need 2 points here. So let's say we have another point. We'll call it the point x1, y1. Then again, we can create the vector that goes from the origin to that point, which would be x1, y1, because the origin 0, 0, right? All right, now what we just talked about just a second ago, where do you think I'm headed with this? Yeah, what's r1 minus r naught? It's going to be the vector connecting these two, right? Okay, so let's see. So if we take r1 minus r naught, we get this new vector, which we will call v, right? And if we translate v up, right, up, it shows that it attached the tips together. Now, is the vector v the entire line? No. The vector v is just part of it, right? It's just a vector. The line is all the points, all the ordered pairs. V is not all the points. So does everyone agree with this? Now, do you agree with this? R1, which is this vector, is what you get when you take R naught and you add it to V. So tip to tail, right? Take the tip of R naught, add it to the tail of V, and you get this result. So R naught plus V would get you to this point. We're starting to generate right here a very, very important thing, all right? Now, what if I took R naught and instead of adding V, I added 2V? Where would I be? Out here somewhere, right? But it would be another point on the line, wouldn't it? What if I took R naught and I added negative V? It would just point me in the other direction, wouldn't it? And I'd be over here, which is another point on the line. So what would happen if I take R naught and add any multiple of V, or I should say all multiples of V? So look, here, what I'm doing right here is I'm changing the multiple of V. So there was just R naught plus V, right? Brought me to that point. And then I could scale it out. Anything in between, right? Anything out there, 1.6, 1.8, anything out there should give me all the points that direction. I could go forever, right? And then I go and I take the negative values and it points me back in the other direction. So do you agree that you can generate all the points on this line by taking R naught and adding to it all scalar multiples of V? All scalar multiples of V. And that's what we have right here. This is the general form of the vector equation of a line. Look, notice the notation. We write r, vector r of t. So it's a function, right? It's a vector function. T is the number sitting in front of v. So t is the what? The scalar that we're going to multiply v by, right? We change t, we change where we are on that line. We change the vector. But all of them require that we start by adding r naught first, right? Go to r naught, that takes you to that first point on that line, and then from there, it's just all the different scalar multiples of v. All right? That's our general vector equation of a line. What is it that we need to know, though? I mean, think about this. If someone says, hey, give me the vector equation of a line, you need to know, God bless America. I don't know what we're going to do. May I go old school? Just get up on the board. You know, I'm starting to think it might actually be my computer or this wire, because this happened in the other class too. So I'm complaining about their technology, and it might actually be my VGA output. I have a wireless display adapter that I can use. I'll bring it next time. Or I might even run to my office if we on our break and grab it, where I can just totally get past using this port. So that might be an option I take here later today. Okay, so what was I saying? The vector equation of a line, R2, is R of t equals R naught plus TV, where t is a scalar and v is the direction of the line, right? The v is an important vector here, right? Very important, because it gives you the direction of the line. And then R naught is what? It's a vector, but where does it come from? From the origin, but what do we need to know what R naught? A single point on the line, right? Just give me any point on the line, right? And I'll be able to come up with what R naught is. How will I come up with V? The direction. What would I need? I need another point, right? Because once I had the 2 points on the line, I could create the vector between them. So it's going to come down to the same thing we need in college algebra. We still need 2 points to define a line. But the way we define it's going to be different. And the thing that's great about this is, as we'll see, this extends to three-dimensional space also. So if our R naught is the vector x naught, y naught, and our v is the vector AB, then if we replace R naught and v, and then just go ahead and distribute a t through here, and then add these two vectors together, we get this. Oh, this is unacceptable at this point. Oh, what do y'all think I should do? Which one? This one? Yeah, it could be. It could be. Okay, let me do this. Let me just bypass